Hello class, I'm Dr. Yang and welcome to cs370 Operating Systems. Condition variable is stateless or memoryless. If signal is called when no one is waiting, nothing happens. What it means is, the fact that signal was called will not be remembered. Let's say this is a time, and you have one thread A, and it was executing. Okay, it was executing something. It entered this critical section. Okay, so grab the mutex at this point, and then it executed some code, and it was determined to wait. Okay, and let's say you have another thread here, thread B. Let's say this is another critical section where thread B calls signal inside here. In this case, thread A, in real time, the wait happened before thread B's signal. So in this case, thread B will wake up thread A. Okay, so the signal at this moment, the condition variable has a valid waiter, in this case the thread A, and this thread A will be woken up, okay, and make progress, okay, like this. So this is one scenario, but what about, let's imagine that somehow there is a race, thread A and thread B, at least in this instance, you don't know which thread executes faster than the other. So it is entirely possible that thread B entered this critical section first. So thread A had to execute critical section code over here and determined you had to wait here. Okay, so if this happens, then thread A will not be woken up, even though thread B here called signal just before. Okay, so this is what I mean by the condition variable is stateless. So basically, when thread B calls a signal, and if there is no waiter at this moment, then this signal will have no effect whatsoever. No effect right now and no effect in future. So again, if signal happens before wait, that signal is not remembered, so the waiter will still be waiting, just like in this case. So you may think that this is obvious. This is too trivial. But the thing is, we need to emphasize the fact that condition variable is stateless, because there's another synchronization object that we haven't studied yet called semaphore. And the semaphore is just like a condition variable. Okay, the behavior is like a condition variable, but the semaphore is stateful. That means the semaphore actually remembers how many times signal happened. Okay, so that's the defining differences between the condition variable and semaphore. Okay, so we're going to study semaphore later. Okay, let's say you're just woken up from wait. Does that mean that somebody called signal on me? The answer is no. So waking up from wait doesn't necessarily mean that somebody called signal. Why? Because the superiors wake up. So this is not a bug, this is a feature, okay? And we went through a lot of examples. I think it's example number 2, number 3, number 4. They all had a provision for guard against this superiors wake up. This is the reason why you need to check the waiting condition again after you're being woken up, because the fact that you are being woken up doesn't necessarily mean that somebody called signal. because it might just be the superior wake up phenomenon happen, and then you're just woken up. To guard against this superior wake up, you are required to recheck the condition that you're waiting on. Condition variable, semantics to remember. When a thread is woken up from wait, it may not run immediately. Okay, so we talked about this already. Why it may not run immediately? Because the thread was in wait state, and if it was woken up, the waiting thread will make a transition back to ready, not to running state. So this is a very important semantics. Again, the reason that I'm making this emphasis here is because there is alternative approach. There is a different kinds of condition variable that actually makes transition from wait back to running. Okay, right. So signal broadcast merely put thread back ready list. When log is released, anyone might acquire it. So this is the reason why you should not expect that the signaling doesn't imply that the signaled thread executes right away. Okay. Wait should be in a retry loop. Again, another emphasis here. You can write your retry loop using while in C, or you can just use a goto statement. So retry. You can write code like this as well. But you may ask, but why this semantic? Okay, so the semantic that we talked about, the behavior of this condition variable, is known as Mesa semantic. The semantic being going back to not running state, but on ready state, and also this pesky thing called superior wake up. Why do you allow this superior wake up? Because it simplifies the implementation of condition variable and locks themselves, and it simplifies the implementation of code that uses condition variables and locks. So it means that not only it benefits the elite, okay, who gets to implement these condition variables, but it claims that it is beneficial to general coders. So this is a quote from Java manual that talks about the superior wake up. When waiting upon a condition, so this is a capital C, this means this is the name of the condition variable, the class of the condition variable of Java. Okay, so when waiting upon a condition, a superior wake up is permitted to occur in general as a concession to underlying platform semantics. This has little practical impact on most application programs, as a condition should always be waited upon in a loop, testing the state predicate that is being waited for. Okay, right off the bat, Java follows the same semantic, and the superior wake up phenomenon happens in Java as well. Okay, but the thing is, why? Okay, why do you allow this? The thing is, it actually promotes to write code that rechecks the condition. Okay, so condition should always be waited upon in a loop. You need to test the predicate even after you are woken up. So that's the mantra, that's the mindset of a programmer who writes the code that waits. Why is this beneficial? Why do you require you have to wait, you have to recheck the condition? Because if you write the code like that, that means your code is tolerable to excessive wake up. You can be woken up more than necessary, and your code, if your code is written like this, then your code will be more robust against excessive or unnecessary wake up, including superior wake up. This is robust, because programs are usually just maintained. When you're writing code, it is important to write code that is easy to maintain. If you're writing concurrent code and you have this wait loop, and you have a condition const wait, let's say we have this kind of wait loop. The thing is, the requirement changes. So for example, this is a version 1.0, and sometimes later the requirements of the program changes, and you have to change your code, change the condition, or change the other parts of the internals. You sometimes need to change the shared state and how they work. So if you write code around this idea where the action of waiting is removed from testing of the condition of the wait, and this is beneficial for maintaining and verifying this kind of concurrent code, because if you separate this condition from waiting and waking up, you can deliver more than necessary signal. This wait can be woken up more than necessary. If you're woken up unnecessarily, that's okay, because you check the condition back again, and if you still haven't met the condition, then you will go back waiting again. So the semantics of a condition variable promotes this kind of code writing. All right, so we're almost done. Structured synchronization guideline. Identify objects or data structures that can be accessed by multiple threads concurrently. So first you figure out the shared state and add locks to object and modules, and make sure you grab lock on start to every method or procedure and release lock on finish. Okay, I have to expand upon this statement. It is technically true that you end up adding lock as if the lock protects the shared state. So usually when you write a piece of code, when you declare a shared structure, so you have for example struct or class, you have embedded lock. For example, if this is a BBQ, you have lock here, and you have buffer, head, tail. So this is the shared state, and to protect this shared state, we added this lock. So it looks like the lock is there to protect this shared state. Okay, make sure that you grab this lock and release the lock when you're done. The thing is, the lock is not directly protecting these variables. So these are the object in memory, right? So these are the variables. But the lock is there to protect code. So usually, you have to acquire, and then later when you're done, you have to release, and the log is there to create this critical section of the code. And you create this critical section, and what you need to do is you need to put codes that reads or write inside this critical section. So the more correct way of understanding the relationship between lock and shared state is that lock is there to protect this piece of code, and this piece of code is the one that has to access shared state. So there is some indirection. So it is very important to recognize that the lock actually protects the piece of code. And this is the critical section. Okay. Back to the slide. If need to wait, so use retry loop. Do not assume when you wake up, signal just ran. This is called the Mesa semantic. the woken up thread doesn't go back to running state. Instead, it goes back to ready state. Okay. If do something that might wake someone up, you need to call signal or broadcast. And make sure that you call signal or broadcast inside critical section. Okay. Always leave shared state variable in consistent state. Okay. Not only when you release the mutex lock, this is obvious. You're leaving this critical section, so make sure the shared state in consistent state, because that's the moment when other thread can grab the lock and access the shared state. But also make sure that when you call wait internally release the lock, you have to leave the shared state in a consistent state. Just like here. So when you're waiting, you actually release the lock. So in between, some other thread acquire the mutex lock and do something, modify the shared state, and then call signal so that the thread A can wake up. All right, recap. Synchronization best practices. Start with mutex locks and condition variables. Don't use semaphore or other low-level constructs such as spin lock. So this means that if you're not 100% sure that you need semaphore or you need spin lock, always start writing your code, developing your code around mutex lock and condition variable. All right, identify critical section of your code and protect it using mutex lock. Again, so this means that the basic structure of synchronization code looks like this. Lock is there to protect this shared state, but lock can only protect a piece of code. So make sure you put the code that accesses the shared state inside this critical section. All right, always hold mutex lock when using a condition variable. Not just wait, but also signal and broadcast. Okay, always wait in retry loop. Never spin wait with sleep. So what this means is, don't write code like this. Okay, so you have while loop and some condition need to wait, and over here you, instead of calling wait or some kind of blocking call, you write code something like this: sleep 10 millisecond. So this is some kind of arbitrary number, and obviously this is sleep as a system call that blocks this thread, and after 10 millisecond pass, then sleep will return and you will check this need to wait condition again. Don't do this. Why? Because we learned how to wait properly. So if you have to wait for an event, you have to either use appropriate system calls designed for waiting for I/O events. These are some of the names of the system calls, okay, for I/O waiting. So select, poll, or epoll infrastructure. So epoll wait is the name of the function. And these system calls allow you to wait for certain I/O events. For example, you are waiting for a file I/O or a network packet to arrive. Use select or poll on the file or network socket descriptor. Okay, that will allow the kernel to block you and have you wait on the file descriptor until I/O event happens. And then select or poll will return when that I/O event happens. So use those system calls. Or use condition variable to wait for program-specific internal events. For example, if you look at the BBQ, you have to wait if the buffer is full and you're trying to insert item. So that's not I/O event, that's program-specific internal condition. So if you encounter that kind of condition to wait, use condition variable.